A is another general technique that comes up all over the place in parallel computing, which is a dynamic load balancing. And so I'm going to review the motivation. I think it's pretty clear you want your program to go faster. It's not going fast enough. And we actually talked about this earlier in the semester, but we had a different name for it. We called it graph partitioning. That's static load balancing. That's where you know everything ahead of time and you can afford to spend a lot of time to make sure that every processor is doing the right amount of work. And I'll just recall that on one slide, but the focus of this lecture is going to be dynamic, where you don't know until runtime what all the workloads are. And you have to work hard to make sure every processor stays busy and not spend too much time doing that. So I'm going to spend some time doing a taxonomy, kind of a spectrum of what are the costs associated with recognizing there's load imbalance and how to fix it. So the task costs are obviously a major part. And they could be quite, but there's a big spectrum there. They could all be the same, and you still have to worry about load balancing. They could be wildly different, small tasks, large tasks. And of course, then there's when you know about them too. Task dependencies could come up. At one extreme, it could be embarrassingly parallel tasks, which is, of course, an easier load balancing problem. Or you could have complicated dependencies among them, and you still have to get things load balanced. And finally, there's locality. So if you have one processor which has to share one task which has to share a lot of data with another task, and you put them far away in order to load balance it, well, you've introduced a lot of communication. So how do you take that into account? Again, the embarrassingly parallel case is the easiest one. So there's going to be this spectrum of solutions depending on when you have all the information you're going to get. And the easiest case is the static case where you know everything ahead of time. And as I mentioned before, we talked about graph partitioning a lot before, so that's the static case. There's the semi-static case, let's say, where you have some information before starting, but a lot of it only happens when you start up the task. At that point, you know what the costs are. And then the most interesting case that I'll spend most of my time on, where you know nothing until the program is running. And at that point, you have to decide how to assign work to different tasks and keep everything busy. And so even in the dynamic case, there's a range of possibilities, which is how fast, as you're creating tasks and assigning them to processors and they finish and then you create more tasks, they're going to have some statistics about how, what they're doing. So how fast are those statistics kind of constant? All the tasks are about the same? Or do they change slowly over time in terms of, which means your load balancing scheme can sort of every once in a while change the way it does it? Or do you get these abrupt changes? All of these come up, and there are a lot of different systems. There's no one best way to do them all, and so there are a lot of different approaches people have taken, and I'll give you kind of a tour through lots of different solutions that people have done. So I'll tell you about how each one of these works. Sometimes people actually prove theorems, making some assumptions about the statistics of the tasks, and a bunch of tools, because a lot of people have invented tools for this. So what are the sources of inefficiency in your parallel codes? Well, we spent a bunch of time about single processor performance. That was homework 1, right? So you got to get that right. There may be too much overhead from creating tasks. You don't want to create a parallel task, do a pthread create to do one floating point operation. That's much too much overhead. And then what we're going to concentrate on mostly here is the load imbalance, which is a different amount of work across different processors. So I should say, why would one processor run faster than another? I mean, the obvious idea is you've given it more work to do. But there's another reason that we have to take into account, which was that the processors may have inherently different speeds, and which can change over time. So if you're using a shared resource, a shared memory machine, and there's other stuff going on, somebody else has part of that cache, then it's going to run slower than if you get it all to yourself. Obviously on a big machine like Hopper, there's a lot of shared resources. But there's also heterogeneous resources, like some processors may have CPUs, old CPUs which are slow, new CPUs which are faster. If you're using all the machines in your lab, there are old machines and new machines. And of course CPUs and GPUs. So there's all these different sources of heterogeneity. Even if it looks the same to you, the machines may feel different. So the question is, how do we recognize that we have load imbalance? We need to do some instrumentation. Yes, question. And I will turn on the microphone.
Just a general question. Are we here inherently talking about, are we assuming a single machine case for the rest of this lecture? Or no?
No. So all these tasks would work if you've pulled together a grid of processors lying around your lab and you want to use them all, these techniques would work there too. The relative cost of moving things around would change. Okay. But the techniques are quite general.
Okay.
Right. Some of them have only been implemented for high-performance supercomputers, because that's that was the motivation. And others are, will run anywhere you can get an MPI job running. So the question is, how do we recognize that there's a problem? So we have to do some instrumentation. And we already gave you some tools for how to do instrumentation. I'll just show you one picture from an older talk. David Skinner talked about this. So this is from Tau, but I think he talked about IPM. So what you can do is automatically insert instrumentation in your code. In this case, there are 4 processors. And there's the horizontal axis is time, and it color codes your processor by the time axis by which subroutine is taking up that stretch of time. So the yellow bar is some very small lettering that I can't read here, so that's the yellow subroutine whose name is given over here. There's a red subroutine whose name is given over here. And the black lines represent communication. A message of some kind has been communicated from, say, processor 1 down to processor 3. So here is the same picture without all of those communication lines. It's maybe a little easier to see. So it's the same color coding up there without the vertical black lines. And so what you could do, you could try to do is look at this and say, oh, there's a bunch of idle time. This is actually a well-balanced program. There is no color labeled idle. So this one is kind of load balanced. But you could look at a picture like this and say, oh, this processor is less busy than the other. And here's another sort of metric of load imbalance. This is a little matrix which says how many words are sent from processor I to processor J. So for every pair of processors, it just counts the total amount of communication. And in this case, processor 1 sent 18 megabytes or whatever that number is to processor 3. So this also can give you an indication of communication imbalance, if one processor is getting all the data and not another. Now, even though there are these tools available, it's not always easy to look at them and say, oh, I recognize that there's a load imbalance. The kind of obvious thing you'd expect is that there's a barrier, and one processor is totally idle up until that barrier, and everybody else is busy or something like that. But you can't always tell. Your code isn't always organized with nice, simple compute, barrier, everybody stops, then you can see the load imbalance. It's often much more complicated and interleaved. And also you may have things like spin locks. You may not call a barrier routine that's recognized by your tool. You may have written it yourself in a shared memory where you keep checking a word to see if it changes from 1 to 0. So it may look like perfectly busy time to the tool, even though it's really wasting time because it's not load balanced. So anyway, I just want to give you a heads up that sometimes it's hard to measure it, but once you do, the question is how do you fix it? I'm going to spend most of my time on how do we fix it. So, and by the way, so there's a bunch of tools for this. The tools that actually collect the data that automatically instrument your code are called IPM and Tau. And then there's a visualizer which builds this picture called Vampire for some reason. Okay, so just to remind you, this is the static case that we talked about a lot before. Just to remind you, I have a graph. And now each node in the graph represents a task that I want to perform. And what I want to do is partition the tasks onto the P processor, so every processor has about the same amount of work to do. So here, I've given each processor an equal number of tasks, but they could be weighted, obviously, if they have different weights, because graph partitioning takes that into account. And I want to minimize communication. And so we talk about many, many different algorithms for this. It's all NP hard to do it perfectly, of course, so we only approximated. So there was spectral algorithms and Kernighan, Lin, and multi-level. And there's good software available like Parmetis and Zoltan. And the thing is, these are even good in the dynamic case. So suppose that you have a task whose balance you don't know ahead of time, but you know a little bit about it because it's going to change slowly over the course of the run. So at the very beginning, you can partition your tasks perfectly, run it for a while until the balance changes. So what do you do when the load balance gets slightly wrong? You don't have to use this entire fancy graph partitioner from scratch to redo it. Remember Kernighan-Lin? What did Kernighan-Lin do? It said, I've partitioned my processes, my tasks, into the left and the right, N1 and N2, and it's pretty good, but not quite good enough. I want to just move as few vertices across the border as possible to make it better balanced. And it did that by a very cheap iteration. And so by just calling this little inner loop subroutine, if you're close to being load balanced, it will get you closer to being load balanced. So some of these tools can be reused even in the dynamic sense. Okay, but you don't want to do it that often because they're still a little bit expensive. So that's the static case, which I won't worry about too much anymore. So let me talk about the spectrum of different considerations about load balancing and so that it's sort of a taxonomy, so you can figure out which technique you want to use. So there's the costs, and the simplest question would be, do all the tasks have equal costs or not? That's the interesting case. And then, when do you know the answer? When do you know the costs? It could be before starting. So in matrix multiply, when I break up my matrices into blocks, I know they're all equal and I know them ahead of time. There's no question there. But that's the simplest case. You may not know until you create the task. So if you're trying to load balance sparse matrix vector multiply, not until somebody hands you the sparse matrix and you know the non-zero structure can you figure out how much a task, a row, costs to do the dot product. And it may be, if you're doing something really complicated like search, discrete event simulation, it's not until the task says I'm done that you know how long it took, right? Because it's a totally dynamic kind of activity. So that's the spectrum from everything ahead of time to you don't know until it returns. Then you have task dependencies, and the simplest case being embarrassingly parallel. Do it in any order you like. But if there are dependencies, again, you may know them all ahead of time. That would be, matrix multiply being the simplest one. It's a nice simple summation. Or you may know it only when the task is created. Or you may only know it when the task ends. It says, oh, I need to send my data to this other task because I figured out what my discrete event has now caused this other discrete event to occur, but I don't know that until I finished executing my little part of the simulation. You also have the case in search that if you're searching one part of the subtree and it finds a good solution there, it can abort the other processes that are looking through other parts of the subtree because suddenly they know that they're never going to do as well as the first subtree. So you have that issue as well. And then there's locality, how much data needs to be shared between different tasks, ranging from the embarrassingly parallel, no sharing, to the expensive stuff where you'd rather not load balance these two tasks if they have to share too much, because then they have to communicate. And even if the properties are known only when the tasks end, there's a spectrum. This was the hardest case, but it may be that there's fixed statistics that on average all the tasks take a certain amount of time, the mean and standard deviation, or that could change slowly over the course of the run, or you could have these abrupt changes. All of these come up and people have built tools for every one of these possible situations. So let me just draw these pictures again to sort of show you what this spectrum looks like, and your load balancing problem could fit anywhere. So here's the task cost spectrum again. And you could have the easiest case is when they all have equal costs and you have P bins, P processors you want to put them in. The next harder case would be the tasks ahead of time. They all have different, so the height here, items means tasks. The height of the bin is how much work it is. And you want to pack these n items in these P bins so they're all equally high, so each one spends an equal amount of time. Even if you only have 2 bins, that's a classical combinatorics problem called bin packing, and it's NP hard. So already we have to give up finding the perfect solution and use heuristics, even if I just have different sizes that I know ahead of time in 2 bins. So we have to use approximations. And the hardest case is we don't know until after execution. And here, as I mentioned, there's search, there's circuit simulation, where one part of the circuit becomes active and then it causes something else to happen in another part. If you don't know that until you simulate the circuit. And even in global climate modeling, GCM, that could happen because you could have a weather event or something going on which requires like a cloud formation. So this processor suddenly gets busy because it has to do more detailed simulation of that cloud, and it takes longer. And you don't know until that storm occurs. Okay, so that's the cost spectrum. Here's the dependency spectrum. Again, the easiest case is embarrassingly parallel. Each little dot is a task. There's no edges, so there's no dependencies. And again, matrix multiply kind of fits in there if you ignore the additions. The next task is when you know the structure ahead of time and there's a nice predictable structure. So you could have a wave front. You're doing time marching. Time t equals 1 depends on time t equals 0. So there's a nice simple dependency. Or you could have map reduce kind of things where you have an out tree where you're searching some tree which is always a fixed binary size. You could be doing a reduction, or you could have a general DAG where all these, there are no loops in here. A DAG is a directed acyclic graph, but it's sort of fixed ahead of time. And all of these are kind of illustrated by matrix computations. In particular, Cholesky, where you don't have to pivot, you can sort of, if you know where the non-zeros are ahead of time, you know what the dependencies are, and you can sort of schedule that ahead of time. And the hardest case is when it all changes dynamically, search being one, or sparse Gaussian elimination as opposed to sparse Cholesky. So what's the difference between these two? in sparse Gaussian elimination, you have to pivot. And until you see what the numbers are and pick the biggest one to put it on the diagonal, when you pivot, you don't know what the tasks are going to be. And so that makes these two apparently similar operations much more difficult from the load balancing point of view. One of the tools I'm going to talk about is called Silk. That's a language that was developed by Charles Lysis at MIT. He did a startup. It was acquired by Intel a few years ago. It sort of is designed to support a subset of this, in particular fork join graphs, which are what these things look like. It does a good job at load balancing those. I'll talk about lots of tools that sort of fit the different parts of this spectrum later. And now I have task locality, which in the easiest case is embarrassingly parallel, no sharing of data, don't have to worry about communication at all, to you share it with some fixed neighbors in some pattern that you know ahead of time, and we've talked about how to deal with that before. And then the hardest cases where the communication pattern is unpredictable, discrete events, you don't know which one event will cause another one, so that's the hardest case. Okay, so that's the spectrum of problems, and they give us a spectrum of solutions. And the spectrum of solutions basically depends on when you know the answer, when you know the input. Do you know the input way ahead of time? That's the easiest case. You do graph partitioning, it's static scheduling. You do something offline. And actually, it turns out that even if you know everything ahead of time, even if you know the entire dependency graph, sometimes people still use a dynamic approach. And why would they do that? It's because the DAG is so big you can't write it down. And so they go ahead and do it dynamically anyway. And I'll show you some tools later which actually choose to do that. Even for dense linear algebra, people are now doing dynamic scheduling just because the DAG is too complicated. So then there's semi-static, where you know some stuff ahead of time, where it changes slowly. And as I mentioned there, you can sort of do a static solution at the beginning and then every once in a while update it. And then there's the dynamic part, which is where I'm going to spend most of my time. Okay. So now to dynamic. So I'm going to just sort of talk about search as an example first to show you why, so searching a tree of different possibilities to just make it clear why things can be dynamic. And then I'll talk about two different approaches that people have used for this. One which is centralized, which is maybe the best solution for a shared memory processor. We can sort of collect all the information in one place and decide what to do. Versus distributed load balancing, where it's all across a machine and you can't afford to bring all the information into one place to make the decision. So, search. Let me just talk about this. They're often very computationally expensive. Imagine, you're trying to play chess. You have a search tree where each node in the tree is a chess board with all of the parts out there, and you're not going to build that whole tree. You're going to search it a little piece at a time. And they have very different parallelization strategies. With physical simulations, as I said, we know nearest neighbors often comes up, and so we're going to definitely do that dynamically. And so here's a bunch of examples. Some of them come from engineering. Where do you put down the different processors on a VLSI chip to minimize the wire lengths between them? That's definitely a search problem. Robot motion planning is the robot walks around the room and somebody walks around it. Depending on that dynamic physical situation, the robot will have to make a different decision about what to do. Chess, I mentioned, speech, and genomics, right? In that case, your search space is, subsets of genes in some order. How do you match them to another string of DNA? That's a very large space. Okay, but let me just go back to search. And so this is what you should think of a search problem as. Here is the original chessboard where everybody's lined up at the beginning. This is a move where you move queen's pawn forward by 2. This is where you move king's pawn forward by 2. So each of these is a different move forward, and then you have alternating moves. And what you'd like to do, of course, is find where you win. This is checkmate, blue, you win, and the red ones are the bad ones where the other guy checkmates you. And so the question is, how am I going to assign work to different processors to do this? And needless to say, I don't know what this graph looks like before I start, and I'm not going to build it all. So we had a lecture, so I have to traverse this graph. And we had a lecture on graph traversal before, and I'm going to assume we all remember what DepthFirst Search and BreadthFirst Search are. And so I will skip this slide, which is a review of DepthFirst Search and BreadthFirst Search. And let me just go on to how those are used to search that particular tree. And DepthFirst Search is actually, all right, when Iden talked about DepthFirst Search, he said it was inherently sequential, and therefore we would do BreadthFirst Search. So I'm still going to talk about depth-first search here because it's possible to go depth for a while, find a subtree, give it to another processor, then back up and go down another edge and give it to another processor. So that's still called depth-first search, but there's still parallelism involved because you don't go all the way down. You go down a little ways until you find a subset of the search tree and you give that to another processor. That's called simple backtracking. So well, search to the bottom, that would be the sequential part. But what you can do is you search down a little ways, you find a subtree, and you give it to another processor. Now, how do you decide whether to do that or not? What you can do is keep track of the best solution you found so far. It may be that you get to a position on the chess game where you say, and assign it a number. This is, this position has value 3 at best. But there's another one which is, there's a position here in this other subtree which has value 4. I'm not even going to bother searching the subtree where the best I can do is a 3. I might as well put all my resources into searching the subtree where it's 4. That's called branch and bound. You somehow need to be able to assign a value to a subtree which says, the best I can possibly do in this subtree is 3, and then you can decide whether to spend any time on that. And then there's something called iterative deepening, which is sort of in between depth-first search and breadth-first search, which is where you search down the tree only down to depth D, and then if there's no solution found, you say, well, I'll go down to 2D or something like that and see if I can do better. And then, of course, all of that can be done in a breadth-first manner just as well. And we talked about how there's much more parallelism in a breadth-first search because there's many children that you can search along. So let me just draw some pictures and talk about the pros and cons about this. So I'm going to talk about simple backtracking. So suppose I have tried to do this statically. So what I'm going to do is here's the root. I have 2 children. I have no idea what it looks like underneath me, but here's what the eventual tree will look like. So I have one tree that I assign to the purple processor, and I keep the other subtree to myself. Since you have no idea what it looks like down here, this could be the load balance that you end up with. And the purple processor has much less work to do than the blue one, and so this is a bad idea. And if I had 4 processors, I could do the same thing. I start at the root. I have 4 processors worth of availability. I have 2 children, so I give 2 processors to each child to continue searching their search tree. So this guy now says, well, one of my processors down to the left, one of my processors down to the right, one processor left, I'll keep myself down to the right. And again, no matter how deep you go in here, the load balance can be arbitrarily bad. So we should obviously do better than this. And so the first approach is better on a shared memory machine, or where you don't have too many processors, and that's where you have a centralized task queue. So what we're going to do is simply keep in one place a list of all the work that needs to be done, pointers to roots to vertices in the tree, whose subtrees, nodes in the tree whose subtrees need to be searched, and every other processor simply goes and grabs whatever the next one is available, and so everybody stays busy. So this is a frequently reinvented, obvious kind of thing to do. Kurt Koitzer mentioned this pattern in his lecture on general patterns. What was his name for it? Do we remember? There are all sorts of patterns we talked about there. Agent repository. That was what it was called back then, where there's a repository of all the different tasks in one place, and then all the agents go off and get work from it whenever it's necessary. So how could this fail? So what are some ways where it could just crash and burn? So if the chunks are too large, then obviously not everybody's going to be kept busy. What if I just divide up the task into very tiny little pieces? Then this is going to be a sequential bottleneck when everybody is showing up here every little piece of time to grab the next piece of work. This is going to be a sequential bottleneck, and there's going to be a lot of communication giving all the workers something to do. So there is no one best way for every problem to divide it up, but on a shared memory machine, this could be a perfectly good thing to do. It could be very fast access to get to this queue. So there's so when this is applied to loops, it's often called self-scheduling. Okay, so the task may be so I was talking about this in the context of search, but you can also think of this in the context as I have a loop for I equals 1 to n. Each loop body is doing some unknown task, and the question is, which loop iterations do I assign to which processor? So that's maybe a little bit easier to think about. So I know ahead of time that I have a loop, and the question is which loop bodies do I assign to which processors? And this has a lot of different approaches, even in that simple case where I have a loop body that I want to assign to different ones. So let me now tell you what the variations are for this sort of self-scheduling. So as I said, what I need to do is decide how much work to assign to each processor from this loop. I have n tasks, and the question is how much do I give to each available processor? And I don't want to give one iteration to each processor because there's just too much contention, as I said at the shared queue. Everybody's going to spend their time going back to this central location and saying, give me one more thing to do. So I'm going to assign some chunk of tasks of size k. So k consecutive loop iterations will be given to every processor. And if k is, as I said, too large, then, well, that's good because I won't have much overhead at my centralized queue, but I may not have a very good load balance. And if k is small, I'll have a good load balance, but I'll have too much overhead touching the guy in the middle. So the question is, how do I decide how many tasks to give each processor when they come and ask? And many people have sort of asked this question over the years. And let me just give you some examples of the sort of history of people coming up with more clever ways to pick how many tasks do I give to each worker when they comes and asks. So the simplest thing you could do is have a fixed chunk size. So if you know enough information about the statistics of all the task sizes, then these two folks, Kruskal and Weiss, gave a formula, a closed form formula for what is the optimal size k number of tasks to give to everybody who comes and asking. So what did they assume? They assumed they had a probability distribution of all the task run times, and they assumed that that distribution had some nice properties, like it couldn't be bimodal. So for example, they had to make some pretty strong assumptions, like it couldn't be like 50% chance it takes 1 second and 50% chance it takes 2 seconds. It had to be a nice sort of continuous drop. And they assumed there was a certain cost of going to the centralized task queue. And so they came up with this closed form formula, which I don't put on the slide because it's not necessarily that useful. It depended on the number of tasks, the time to access, the standard deviation of the runtime, and how many processors you had. You multiply all those together to the 2/3 power and take some logarithms, and that was their magic formula. Anyway, it's not that useful in practice, but if you make enough statistical assumptions, you can write down a formula. So what do we do if we don't have all that statistical information? The next kind of variation, which is much more practical, is something called guided self-scheduling. And the idea is pretty simple. At the beginning, I'm going to give everybody a lot of work to do so that they don't come and ask me very much. And then, as I get closer to the end, I'm going to give people smaller and smaller chunks. And that way, things will kind of balance out more closely, and people will finish, more closely at the same time when they're all finished. So the question is, big chunks of work at the beginning, k is large, smaller chunks at the end. How do I choose k? And the intuition is really simple. You simply count how many tasks what is the total number of remaining tasks I have at any time, divided by p, the number of processors, and that's how much I'll give away. So if I have 1,000 tasks and 10 processors, everybody who comes asking, I'll give them 100. But near the end of the run, when I only have 20 tasks left and 10 processors, I'll give everybody 2 when they come and ask. And so that way it'll gradually decrease from 100 down to 2, and everything will balance out nicely. And there's a paper written on that with lots of simulations that shows that it does a pretty good job. But intuitively, it seems like a reasonable thing. So that inspired another paper where, in addition to taking into account how much work is left, they used some statistics, and they said, well, not every task is going to have a completely predictable runtime. But what if I know the statistics? What if I know there's a sort of the mean and the standard deviation of all the task sizes? So if there's a big variance in the task sizes, if there's a big variation, then I should give them fewer of them, right? Because it may not balance out so well. You may have a high chance of getting a few big tasks. But if there's a low variance, and you can afford to pack more of them together because you're much more sure how long it'll take. Right? And so again, there's a sort of a formula written down in this PhD thesis from some years ago, and there's a bunch of experimental results and theorems, and it's very similar to the simpler case, which I just told you about, and sometimes it does better. Okay, so that's yet another variation. And the final variation people explored is, well, what if every processor is not the same? Some processors are running faster than others, and there's a pretty obvious weighting mechanism that you should do, which is that if one processor is running slower and you have to decide how much work should I give it, you weight it by how much time it's going to, how fast it's going to run. So why would this come up? And why would one processor run faster or slower than another? And this was invented back when people had systems where they took all of the machines in their lab, some old PCs, some new PCs. The old ones were slow, the new ones were fast. Also, somebody might be using one of them. It was running really slowly because, surfing the web at the same time. And whatever was happening at that moment, it would keep track of the statistics and assign it the right amount of work according to its, speed at that moment. And so that's yet another balancing mechanism. Okay. So those were the 4 ways of doing centralized scheduling. And so when is this a good idea? And so just to summarize here, it's a bunch of tasks when there's no dependencies on them, so I can assign anybody to any processor, and I don't have to worry about communication. When I don't know the cost of a task necessarily, and when locality is not important, and when the cost of centralization is small, of having this centralized work queue is not a big bottleneck. Okay, so that is sort of a summary, and now what I want to do is give you an example of a system which incorporates a bunch of this and is reasonably widely used. So this is the language Silk. So Silk stands for a language of the C ilk. That's where the name comes from. And this was originally a research project at MIT with Charles Lyserson, and who did a startup which was acquired by Intel a couple of years ago. And so it incorporates some of these mechanisms that I was just telling you about. And so I want to tell you a little bit more about that. What happened to my mouse has disappeared. Just a moment. Okay, there we go. Let me bring it back. Yikes. Okay, let me start again. You can read my mail in the meantime. Okay, let's try it one more time. Okay, so needless to say, there are many different applications that have been written in this to prove the point that it's a good load balancing scheme. But just to keep it simple, let me do a really simple problem, which is Fibonacci. In fact, I'm going to use the worst possible implementation of Fibonacci, which runs in exponential time, just to illustrate it. Okay, so I want to compute fib of n, which is the sum of fib of n minus 1 and the fib of n minus 2. And I'm going to call both of those, recursively. So we all know that's a bad way to do it. The cost of running this algorithm is equal to fib of n. Okay, so how would you take this nice simple C code and change it to run in Silk? You'd put the Silk keyword in front of that subroutine name. And then whenever you called these two independent subroutines, you would put a spawn in front of it. And this keyword simply says that please run this in parallel on any other available processor, and please run that in parallel. So it's very pthreads-like, except it's all embedded in the language. And then there's a synchronization. You can't get past here until these two have finished, and then you return x plus y. So the point is this code will run on a sequential computer. It will just generate standard C code. This will be a regular old, call to a subroutine that will go on a stack that will be eventually executed. And any Silk code will run in plain old C, and any C code is a subset of Silk. So it's a nice simple extension of that. There's no new data types or anything like that. So the reason this is at all reasonable is that the runtime system is very clever, And when you do a spawn, it actually doesn't create a thread. It actually just puts it on the local stack, and the cost of calling this fib subroutine is no more expensive than a plain old subroutine call. The only time you would notice the cost is if another processor has to come and steal this work from you. So the way Silk does load balancing is that it does it by work stealing. So every processor just puts all of its local subroutine calls, spawn subroutines on its local stack, and it costs no more than a standard execution until somebody comes and steals it and has to move the work. So let me give you an illustration of what that would look like. So let me just call this subroutine on Fibonacci of 4, which is reasonable. And so one processor is going to call fib of 4, and it's going to spawn a particular activity. And so it's going to call fib of 3. This will now be stolen by another processor, and which will now be fib of 3. In the meantime, the first one goes on to call from the purple call down to the red call. So this will be fib of n of 3. Okay? So each of these animations is a time step. You can, a virtual time step. So fib of 4 called fib of 3. It went on and called fib of 3 here, which called fib of 2. At the same time, this fib of 3 called fib of 2. Then the next time step is everybody moves one step ahead in this. And I have many calls to fib of 1, which are flying at the same time. I finally get to fib of 0, but now finally I get some returns. So fib of 1 returns, because it just returns a 1. And so it's waiting for a synchronization to occur. And so finally at this point, this call I've gotten to the sync. It is called fib of 1, fib of 0. They're both finished, and I return, this blue dot is now computed x plus y, and it's about to return it. So in the next step, this guy gets returned. This guy is waiting. In the next step, finally, that one gets returned. So that is sort of the time step through the algorithm. And if I had enough processors to do all of this, it would all happen in parallel. But if I only had one processor, it would have happened sequentially on a single processor. So and all of this DAG unfolds dynamically. And, initially, this is only called on one processor. The other processors are doing nothing, and they start trying to steal work from the processor in the center. So initially, the load balance is terrible. But as the thing runs, the work dribbles out of the main processor, and everybody ends up being busy. So that is the model. So it turns out there's some theory you can write down, very simple theory that says how well this does. And it depends on the stealing mechanism. So they had to get the stealing mechanism right. So let me just remind you, we saw this picture before to just define the terms. So here is my DAG, which I'm going to be executing. So have to do that one first, then that one, and then its two children, and so forth. And so T1 is going to be the total amount of work, the number of vertices here. And T infinity is how fast I would run. And so it's the time it would take to run it on one processor, if you like, assuming all of these take time 1. And T infinity is the time it would take on P processors. And that is called the span. It's the longest path between the root node and the final one, right? So the T infinity is that length. And as we talked about before, it's simple to say how fast I can possibly go. If I have P processors, then I can't possibly get more than a P-fold speed up. So the time on P processors is no better than 1 sped up by P. But also, because I have to do all of these processors in order, I can't possibly go faster than the length of that path in yellow. So the time on P processors is always bounded below by the time on infinity processors, which is the length of the critical path. So what I want to do is come up with a simple lower bound for how well Silk does compared to these lower bounds. And so let me just remind you of these definitions. So T1 divided by TP, which is at most P, that's a speed up. And if you're close to P, it's called linear speed up. If it's equal to P, you have perfect speed up. And occasionally it can be bigger than P in practice because you have more cache, perhaps. But in this model, that'll never happen. The speed up is always bounded by P. And the best you can have is T1 divided by T infinity. That's sort of the available parallelism, because we know we have to do that path, the critical path, sequentially. So that sort of gives us an upper bound. So how does Silk then work? It does something in a greedy fashion. So a thread is called ready if all of its predecessors is executed. So over here, this one is ready, and that one is ready, because each one has one predecessor that's executed. But nothing else is ready, right? Because this guy is obviously, he's not ready because the one above him isn't. But neither is that one, because even though these two inputs are ready, the one right above them is not. So the only ones that are ready are in red. And so what do I do at each step? If I have, sorry, went too fast. So if I have at least P of these red dots, at least P threads ready, then I can run them all. And that's what Silk will do. But in this case, if I have 3 processors but only 2 are ready, well, I will run them, and that's the best that I can possibly do. Okay. So how does Silk, take that into account? As I said, it does work stealing. And so what the data structure is that each processor, here are there 4 of them, is going to maintain a work deck. That's a double-ended queue. So a double-ended queue means basically you can insert and take off tasks at either end. And the mechanism it uses is that locally it works just like a stack. So if there's only one processor, you push stuff on the stack, as you create tasks, and you pop them off the same end of the stack in order to figure out what to do next. So where do you steal from? You steal from the other end. So when this processor who has nothing to do, his stack is empty, and he needs to steal, what he's going to do is pick a random other processor and say, do you have any work to do? And if it does, he'll take them off the bottom, whichever end is the bottom, as opposed to the top. So that's going to be the scheme that Silk uses. So given that, what can you prove in terms of how well it does? Okay, so here is the theorem that it does. This is all big O. I won't worry about the details. So this work stealing scheduler gives you a running time of the following. It's bounded below by the best speed up you could possibly have, the time on one processor divided by P, plus big O of the critical path. Okay. So we know you have to be at least the critical path, no matter how many processors you have, and we can't do any better than this perfect speed up, so it's the sum of those two with a hidden constant. So how do you do a pseudo proof of that sort of thing, assuming that this work stealing scheme works well? So there's 2 things to account for. Each processor is either spending its time working, doing useful stuff, or stealing from its neighbors. Right? So I'm going to have 2 sums. And as long as all the processors are busy all the time, as long as the stealing is, keeping everybody busy, then the total amount of time is going to be T1 divided by P, at least that much, right? If everybody's busy, then that's, and the load balancer works, that's what happens. So the work time is fine. Now, what about the stealing time? How much time is spent, asking other processors for work to do? So every time a processor goes off and tries to steal and get something, the chances are 1 out of P that is going to reduce the span by 1. So one processor is going to have the next guy on the critical path, and the chances he gets stolen is 1 out of P. So the expected cost of all the steals is reciprocal of the chance that you get reduce the critical path times the length of the critical path. So P over T infinity. And since the P processors are doing all this, the expected run time is do all the work, T1, plus P time, the time spent. So this is the time spent working, the time spent stealing. Everybody's busy, until the very end. They all stop at the same time, divided by P, and you get this speed up cost. So this accounts for the working, and that accounts for the stealing. So that's a very rough sketch of why it seems to do a good job. So the other criterion for is this a good system or not is not just do they all end at the same time, but do they use a reasonable amount of memory? Because if everybody is stealing from the neighbors, you may end up with way too much memory on some processor. And so the worst case is that every processor, one processor sort of builds this enormous work queue, and everybody grabs pieces of it, and the amount of data is proportional to the total size of the DAG. So we want to avoid that. So we know that one processor will use at most the depth of the tree, right? So if you take that DAG and you push stuff on it, and you say, what's the most stuff I could ever push onto the stack if one processor did it? I know I have to use at least that much memory on one processor. So the question is, what's the worst case? And the worst case is everybody has a stack of the same depth, as though that were one processor doing it. So S is the stack space for doing it on one processor. And so the worst case is that everybody has a copy, basically, of that. So P, the total space would be P times the stack size on one. So that's the claim. And there's again, sort of a hand-wavy proof of that. And it's by induction. And so the idea is that every processor who's working is going to have only a part of the stack, and its own. Let's see if I can. Yeah. So the worst case would be this entire DAG would be on one processor. That would be too much. What I want to show is that no single processor can have anything more on it than the depth of the deepest stack, which is the distance from the top to the bottom of that call tree. That's what I want to prove. And here I have 3 processors. And the point is that each processor can only have a subset of the DAG sitting on it because of the way the stealing works. It can only have a path from the root down to the bottom. And that is bounded by the size of the stack on one processor. So nobody can have a depth of the stack more than 1. Okay, so that is, if you like, a very hand-wavy proof of why the memory is reasonably bounded to, and you're not going to go, run out of memory by running the system. Okay, so it doesn't solve all problems. In shared memory, it's a reasonable tool to use. Okay, so, but it didn't pay at all attention to locality, right? When I went and stole a task, I just was worried about keeping myself busy. I didn't worry about dependencies. So there's a lot of other systems which try to worry about, which people have built over time, and I'll give you a little tour of them, where people have tried to build DAG schedulers that try to respect all of the structure in the DAG. And some of this work was designed by collaborators, Jack Dungera at the University of Tennessee, for dense linear algebra in particular. It has since grown in its scope. The original DAG scheduler that they built was called Plasma, and it was for building this synchronization avoiding linear algebra, so to minimize the number of times that a task had to go say, are you done yet? Now, that assumed that you could build the entire DAG ahead of time and then have it available to you and then schedule it perfectly in a static way. That turned out not to scale all that well. And so what they've built instead, and I'll show you some pictures, is a system called Quark, which tries to do it dynamically. So even though it's dense linear algebra, you'd think you could write down the DAG explicitly. They've chosen to do it dynamically because it's too big. There's another system, and I'll tell you what the interface is too. There's another system at the Barcelona Supercomputing Center, and it's compiler-based. So again, it's a little bit like Silk. It's a language extension. You write down a bunch of subroutines. You say a subroutine can be assigned as part of a DAG. The question is, where does a DAG come from? Well, you insert some pragmas into the code, and you label your inputs and outputs, and it figures out that this subroutine needs this input from that other subroutine's output, and it builds the DAG automatically by, as part of the compiler technology. And so that's a tool that people have used. There's another one called StarPU, which was, and so this is again a shared memory system, and it's, as you can see, people are trying to get it into OpenMP. The next version, as I say, many of these ideas occur to many smart people, so there's some reinvention here. Trying to incorporate GPUs too, which are the fact that some subroutines will run well on some processors with GPUs and other ones won't. They run at different speeds. And some of them are trying to work on distributed versions where you can't afford to have the DAG on one processor, and so the DAG is a distributed data structure and you still need to schedule it. And Intel has introduced its own threading building blocks for this purpose, and so many people there's a lot of innovation going on right now. But let me just show you one of these in a little bit more detail. And it'll be dense linear algebra. And so these are pictures of the DAGs that come up when you're trying to invert when you're trying to do Cholesky factorization of a symmetric positive definite matrix and then compute the inverse. And so there's a bunch of subroutines. So here are 2 different ways of doing it, and a better way and sort of the simple way. So each of these little colored blobs represents a subroutine call to a sequential LAPACK routine. Either do Cholesky in a little block, or invert a little triangular block, or do a matrix multiply kind of operation. And so, it's somewhat visible. So this would be, for example, the Cholesky factorization of the top little corner. And then once you've done that, you can do matrix multiplies of various kinds on sub-blocks that are below it. And anyway, so that's the DAG of one of these calls. This is the DAG of the triangular factorization. And this is the DAG of the more update the rest of the matrix multiply kind of thing. So the question is, if I were to schedule each of these independently, then how much time would it take? Well, suppose I have t blocks in the column. So suppose I've broken my column into 4 blocks. Then if I count, what's the critical path here? The critical path here is 7t minus 3. T equals 4 here, so it's 25. If I count from the top down to the bottom, what's the longest path? The length is 25. Now, what if I take that entire DAG and don't bother with the fact that, and pretend, well, there is no barrier here. I mean, there is a dependency from there to there, but there's a lot of processors that are idle here where I could start some of this work. So let me just take the whole DAG and put in all of those dependencies and schedule it all in one big mess, okay? Which is what this system does. Then the length of the critical path drops from 7 times the number of blocks minus 3 down to 3 times the number of blocks plus 6. So the critical path here is of length 18, and this is what you would like to schedule, right? And so what you'd like to do is have all of these subroutines, run. Have the system create the DAG for you and have this be what your machine is doing without you having to worry about it. And so that is what Quark does. And so what your user code is going to do is whenever you call one of these subroutines, you're going to have a wrapper around it which says, please insert it into the DAG. And it'll have little pointers to say, I'm depending on the input from this other subroutine, the output from this other subroutine call, and here are my outputs that are available to somebody else. Then Quark will build the DAG for you and do the scheduling, and there will be worker queues. These would be the other processors that are trying to grab stuff from the DAG. And in addition to worrying about load balance, which is what Silk worried about, this will also worry about locality. So it tries to balance locality, the fact that one guy's output is big and there's another guy's input, with keeping everybody busy at the same time. So the API, you would take your shared memory code and you would annotate it with just a few subroutine calls so that Quark knows what to do. So you would basically, whenever you were going to call a subroutine call, you would pass in the name of the subroutine, the arguments, and you do Quark insert task. So it's a fairly simple interface to take your original code and make it available this way. So I'm going to show you some performance data in a moment. But let's just ask ourselves, how scalable this is. Okay. So let's suppose that I go back to this picture here, which is I'm taking a dense matrix operation. So it's an n by n matrix. I'm going to break it up into blocks, and so there are t blocks in a column. So suppose I take the matrix n by n, I break it up into b by b blocks, and so there's t equals n divided by b. That's how many blocks are in a column. So how many vertices, roughly, big O sense, are there in this DAG for doing dense linear algebra? So altogether I'm doing n cubed work, right? Each of these little blocks is doing roughly b cubed work. It's doing dense linear algebra in little b by b blocks. So how many of these DAG vertices are there altogether? N divided by b to the power 3 cubed, yes. So this is a really big DAG. So if I take my n by n matrix and I break it up into b by b blocks, then it's the number of blocks in each direction cubed. That's the size of the DAG. And so if I have a measly little 10,000 by 10,000 matrix and break it up into 100 by 100 blocks, which is pretty good for getting BLAS performance, I'm talking about 1 million vertices in that DAG. So this is not going to scale all that well. So the original system, Plasma, did try to build this whole DAG and scale and schedule it very carefully. Quark, on the other hand, does not. It only builds sort of the frontier of the DAG, right? It sort of builds a little part of the next DAG, which is what are the next 10 tasks that I need to do along the entire frontier, and that's what it tries to schedule. And that is a much more scalable kind of thing to do. And so if you can imagine, if I go back to this picture, then it would sort of take and build, let's say, the top of this tree, execute it. Then it would take the sort of the next layer, schedule that, execute it. Then it would take the next layer, and so forth. And that's the way it would work. So let me just show you some performance data. And so this is going to be dense linear algebra, Gaussian elimination, on a 12-core Intel platform. And I'm going to compare 3 different systems. The horizontal axis is dimension. So bigger matrices over here up to 20,000 by 20,000. And vertical axis is gigaflop, so up is good. And I'm going to compare the blue line is MKL, and the green line is quark, and the red line is you build the entire DAG ahead of time, pay for it, and schedule it statically as best you can. So it's the best that DAG scheduling can do, even if it doesn't scale up totally. And on 12 cores, it's really hard to beat MKL, right? Because they've tuned it so carefully. Okay, so let me go a little bit bigger. Let me go up to 24 cores. So it's the same experiment, and I'm hopefully going twice as fast because I have twice as many cores. I'm still only going up to 20K by 20K matrices. And now, the new system, which does the DAG scheduling, is better, at least up until 10,000, and then MKL takes off again. And doing it dynamically, where I only schedule a little bit of the DAG, does about as well as where I have the whole DAG. So one more experiment, where I go up to 48 cores. This is all shared memory, and now MKL is struggling to keep all 48 cores busy, whereas the two DAG scheduling schemes are scaling much better. And so what is the peak on this one? So this is a 48 core, so 8 times 6, this is Opteron, and the peak is 538, and we're getting on the order of 200 out of that. Okay. So this is, there's a lot of tuning parameters in this business, and so it's very sensitive to the task size, so which is, the block size in this case. So. And so if in the plasma case, if I choose very small time, and here's a plot that shows you what the performance is as a function of, and this is so small I can't read it on my screen. So that's NB, so that's the block size. I'm going to break the matrix up into NB by NB blocks, which goes from 0 up to a few hundred. And the vertical axis is speed, so up is good. And so the question is, I want to be up here. If I pick the block size too small, I'll have so many tasks. There's going to be this amount, too much overhead in assigning lots of little tasks to the processors. If I pick the task size too large, I get a different problem, which is the load balance is bad. And so, and the blue line is, again, too small for me to read here. Sorry. So the blue line is plasma, and the red line is quark. And so they both peak out at roughly the same place. And so the question is, how would you pick that parameter? It turns out the block size of 200 is about the best. So how do you do auto-tuning for this business? That's a good question. So this is still all centralized. There's a master, which everybody goes to in this shared memory implementation to get all the work, the centralized task queue. That needs to be fixed to make it scale up to many, many different processors. And again, these experiments have only gone up to 48. So it could be a lot bigger. And just to show you, one last slide on this. If you take this code and run it through the tool that I told you about at the very beginning, which sort of gives you a trace of what each processor is spending its time, this is what it looks like. So here are the 48 rows corresponding to the 48 cores, and it's all color-coded by, am I busy doing something useful? And so you can see that everything is pretty well packed together out to the beginning, but then it gets a little bit sparse out at the end because of the dependencies, that it's not all totally packed together. But it's done a reasonable job of keeping all the processors busy at the beginning, but could be improved out there by packing all that together in a better way. Yeah, so this was 48 cores in a 5,000 by 5,000 system. So these are the sort of tools that people look at to see whether they have done a good job. Okay, so that's all the centralized task queues, shared memory. And I want to go on to the distributed case now. Okay, so they're called distributed task queues, but it's really not a queue anymore. It's just sort of a bag of stuff. So you want to go grab stuff from it, and order is we're not going to worry about, right? So this is all going to be sort of embarrassingly parallel kind of stuff. And so why do I want to do that? Well, if there's no dependencies, it's a good idea. But in particular, in distributed memory, thousands of processors, I can't afford to have a central task queue who owns everything. So the question is, how do I avoid that central spot and distribute the work? So what I need to do is have some sort of mechanism to do either work stealing, one processor has to go to another processor to get work to do, or pushing. Somebody is too busy, he has to give away his work. So the question is, how do you build such a thing? Many people have given names for this. So here are two processors, And and the question is, how would you do this without having, deadlocks and so forth? Because, you don't know when to expect a message from your neighbor saying either I have work to do or please give me some work. So here's the way it works. This processor is busy. Every once in a while, so he's going to do a fixed amount of work, call, a certain number of subroutines of a fixed size, and then go say, are there any messages either asking for work or, or trying to give me work? This guy is idle. And if the answer is, there's a message, I'll take care of it. Otherwise, I'll go back to doing real work. Here's an idle processor. So in this case, it's work stealing. So what he's going to do is select a random processor and request work. And then go back and wait for messages, so do receives. So this is sort of the scheme of what is going on in these two processors to try to balance the work. So the question is, what mechanism should this guy have for selecting a processor and requesting work? What is the right scheme for deciding how to do that? So how do you pick a donor? And there's three basic techniques that people have proposed over the time. The simplest one, perhaps, is round robin. So everybody is going to keep a pointer. So the kth processor keeps track of the target sub k. And whenever it runs out of work, it requests work from that target. So what does it do the next time? It goes on to the next one. So it just goes round robin through all the processors, asking them all in order. So it goes from target sub k to target sub k plus 1, and loop around when you hit the total number of processors. So the perhaps better way to do it, which would be make sure that no processor is skipped, is to keep a single target. Processor 0 keeps a single target. And when anybody needs work, you do round robin on that. So you go to processor 0, you get the single pointer, and you go from target to target plus 1. That sort of makes sure everybody gets asked an equal number of times. But there's a bottleneck, right? If everybody has to go to processor 0 to get the single target. And so even though people did this for a while, it obviously has had its problems. So a lot of theory this motivated a lot of theory to say, let's just pick randomly. Let me just pick a random processor and try to steal from it. And there's going to be a bunch of theorems that people proved, which I'll just quote, which say that picking randomly is just about as good. With very high probability, picking randomly will do just as well as this round robin stuff, which tries to be fair in a deterministic way. Okay. So let me see how I'm doing here. So let me go on to this slide. So here are the results, which say how well does randomness work. And the first time people tried to do it was, let's assume all the tasks are completely independent and they're all equal size. That's the easiest case where people started. So in that case, what we're going to do is not work stealing, but work pushing. If you have too much work, I'm just going to give it to somebody else. How am I going to give it to somebody else? I'm going to pick a random other processor and just give them the work. So you can think of this as picking n balls and throwing them into n random bins. And the question is, what's the most amount of work that any one processor bin could end up with, right? Ideally, everybody would end up with 1. That would be perfect. But I'm doing this randomly, so what is the probability distribution of the fullest bin? That would be the worst load balance. And the answer is, it can get up to log n over log log n. So the worst case would be that one guy is doing log n work and somebody else is not doing anything. So that's not too bad. So then they said, well, I want to do even better than that. So what I'm going to do is I'm going to pick d random bins and pick the smallest one. So I'm going to pick d random processors, ask how much work do each of you have to do, and then I'll give the least busy one the work. Then it goes down from log n over log log n down to log log n over log d. All right? So it's logarithmic, it's exponentially even better load balanced. So all you have to do is ask two processors, make d equals 2, and it goes from log n down to log log n. So you get log log n is a constant for all intents and purposes. So the load balance is quite good. So people said, okay, what if I, instead of picking n balls, and throwing them one at a time, there's parallel throwing. And so the basic result says that if I do this random throwing of equal sized processors, what do I need to have a good load balance? I mean, if I really had n tasks and n processors, somebody would be not busy at all. But if I do this and I have a lot of tasks, then it'll be pretty well balanced. So if I want everything to be well balanced within some small constant, how many tasks do I need to throw out randomly? And the answer is p log p tasks. So I don't need to have too many more tasks than I have processors in order for randomness to keep it pretty well load balanced. Okay, so this was the simplest case. All the tasks are the same size and they're independent. And so then people said, okay, well, what if I have a more complicated situation? The tasks don't all have to be the same size, and they don't have to be independent. I still want to be random. How well can I do? So back in the 80s sometime, Karp and Zhang proved the following theorem. They kept all the tasks in equal size, but now there was a tree. And the idea is that the parent has to be done before the children, but you're allowed to then throw your children into random bins. And so the children, and so their algorithm was, you get all your children and you throw them to random processors. And the answer was, you get about the same answer. So even though it's a tree, this randomness works pretty well, and you still get this nice load balance. So this first case was, all the tasks are the same size and they're all independent. So now all the tasks are the same size, but you got a tree. So the next thing people did, and this was actually the idea in Silk, was the tree is fixed, but the tasks can be variable. They're not all necessarily the same. And so now I have the two options of pushing, I throw it away to a random processor, or stealing, which is what Silk does. So now I'm going to pick a random processor and grab it and bring it to me. And again, they proved that that was a good idea. It's better to receive than to give, you could say. And you saw some of the theory before, and this also, with high probability, gives you a very good load balance. So now, let's see, so we've kept the tree, it's a fixed task tree, and we've now weakened the assumption so we have variable costs. And finally, the end of this theoretical road was the tree is not fixed, it's sort of dynamic as you go, and all of the task costs are variable again. And by doing and what he did was pushing instead of pulling. So throwing out tasks instead of stealing. So his locality was worse, but he showed that, again, you get with high probability a good load balance. So these two are kind of similar, in ideas. So when would you want to use one and the other? So the basic difference between these two is that one is using stealing and the other one is doing pushing. So what do you think the trade-offs are? I mean, theory aside, they both say they work pretty well on average. But what are the trade-offs between better to receive than to give versus vice versa? So if you do stealing, then locality is preserved, right? Because you're not going to, you're only going to grab more work when you're empty, right? So you're not going to take your task and give it to somebody else and send all the data, right? So stealing is better for locality. But what about load balance? So suppose there's only one processor and it starts with all the work, right? You call a subroutine. So all the work is on one processor. Would it load balance faster if that processor threw work off to random other processors, or for other guys to randomly pick processors and steal it when they happen to hit the one guy? It's pretty clear that the one guy with all the work, if he starts sending it to random processors, that'll much more quickly load balance than if other people steal from random processors, and there's only one guy who's busy at the beginning. So there are these different trade-offs, and anyway, Silk has done well, but they both are available. There is no one-size-fits-all. Okay, if you want to read about implementations of some of these distributed task queues, here's where they all are. So let me just think about what time I have left. Okay. So let me just say a few words about two more short topics. One of them is called diffusion-based load balancing. So far, I've been saying you pick another random processor and you throw the work over there. Now, on real distributed memory computers, it could cost a lot more to send somebody a message, work to somebody far across the machine than to your nearest neighbor. So what if we restrict the load balancing to just talking to your nearest neighbors on the network? That's what diffusion is about. So why is it called diffusion? Well, what is diffusion? A little bit of stuff leaks from one point, to another point nearby, so it's the same idea. So if you imagine you have a two-dimensional grid of processors, a 2D torus, what you would do is you would talk to your neighbors, your north, south, east, and west neighbors. You'd say, do you have more work than I do? Let's split the difference. and you'd sort of average with your neighbors. That's exactly, in fact, Poisson's equation. And it's in a discrete sense. You're just sort of balancing with your neighbors, and you just keep sort of doing averages with your neighbors. And there's a bunch of theory about how to do this well, and it turns, not surprisingly, into a Markov chain with a graph Laplacian, and all of the theory we talked about earlier in the semester can be used to analyze it, and over time it does converge to a perfectly flat layout, and there's a paper written in 1996 about that. And you have to sort of pick the right way to balance it, because otherwise you can get oscillations, things bouncing back and forth between you and your neighbor. But if you sort of weigh it slightly so the diffusion is damped, if you damp the diffusion, then it sort of balances out nice and slowly. Okay, so that's what diffusion-based load balancing is. And I'd like to close with describing one more software system, which is widely used. It was developed at the University of Illinois by Sanjay Kale, who's the source of these slides. And it's called Charm++. And it's sort of a framework which has lots of these different load balancing systems built into it. And so you can choose to use it if you want. And it's, so as I said, has many of these things are built in. It has, the basic assumption is that the load balance, the work that you have to do changes slowly over time. So that you can start by load balancing it one way, and you have some statistics. The tasks are going to be run with a certain standard deviation, a certain randomness, but it's going to change slowly over time. So every once in a while you have to do rebalancing. And so that's called the principle of persistence. The things change slowly, so you don't have to intervene very often. And so what it does, its runtime system is going to collect statistics over the course of the run. It's going to keep track of how long each task takes and who's talking to whom. And every once in a while it'll say, oh, it's time to reload balance. So it tries to sort of do all of that for you by having the runtime system keep track of it. So this is, as I've said before, it's going to keep, it's going to assume that the communication pattern and the loads, the sizes of each task change slowly over time. There may be an abrupt change. In that case, it sort of has to start over again. If you hit a different phase of your computation, it'll have to do something expensive, but most of the time it'll be slow and small changes. And so it assumes basically the recent past is a good predictor of the future. So the runtime instrumentation is going to schedule the objects, and it's going to build a database of the communication and computation costs that it's going to use to decide what to do next. So, and every once in a while, it's going to decide it needs to load balance. And so you can decide, because there's no one best way to do it, should it pay attention to the communication graph? Should it try to respect locality? There's a switch for it to do that. Or should it just sort of keep track of how many times each object is, the number of tasks if the communication doesn't matter? So because no one size fits all, so these are all available. And it's using a centralized strategy right now, and it can do graph partitioning, it can do greedy strategies, and you can define your own. If you have a new one of these schemes that I've talked about that's not in there, you can add it. You can put in your own mechanism. So this is sort of a timeline of the way a Charm++ run works. So the horizontal axis is time. So you'll be running for a while, and then it decides, I'm going to collect some data. So it's going to turn on the runtime system and collect data during this sort of red time interval and keep track of what each processor is doing, what all the tasks are. Then it'll say, okay, the load balance isn't so good. It's going to work very hard for a little while, shuffling processes around until it gets the load balance good. And then it'll instrument it to make sure that it did a good job, and then it might have to improve it slightly. At this point it says, life is good, let's just run at full speed ahead for a long time. Let's run at full speed ahead for a long time, the load balance is good enough, and then after a little while later it says, well, maybe I better check. Let me instrument the code again, collect more data, and decide whether I need to improve the load balance slightly. And then you can go full speed ahead again. So no one size fits all, right? It kind of depends on your application as to how often you want to do all of these different things, but it's all there. So one thing it has to worry about is it's specifically designed, I think I said this incorrectly before, it is specifically designed for large machines to scale up. It tries to avoid having a central repository, but it has to get information together on a local scale in order to do load balancing. So the question is, if you have a huge machine, how do you avoid the central bottleneck? And in particular, it only wants to talk to the nearest neighbors. Same motivation as diffusion. So what it does is it has a hierarchy. So let me just skip this animation here. So what it does is that it assumes that there's a task graph, and it does balancing within the children. So let me skip ahead here. So what it will say is that I have a subset of the machine which is operating on this graph. I will balance just within that subset of the machine. And this is running on a different subset of the machine. I will just try to balance there. And I only have to share information about the cost of the graphs within this subset of the processors and that subset. Now, the root here, every once in a while, they'll talk to the parent. And the parent will say, these children are not balanced. I have to help my children. But it doesn't have to talk to everybody. It only has to talk to the roots to get the summary information. At that point, it may say, OK, something has to be transferred from this child to that child. So it tries to do the load balancing in a hierarchical fashion to avoid a centralized bottleneck. Let me skip ahead here. OK. So as I said, it tries to take advantage of the fact that nearest processors are connected to one another. And so in particular, if you have nearest neighbors 2D torus, it's going to be square subsets of that torus, which are going to be executing that algorithm I just showed you, where they share information and try to decide who to move processors to. And only if the northwest corner is totally imbalanced with the southeast corner would something move from the two corners to the other. OK. So let me skip ahead to a performance plot and just show you how well this works. So this is the number of cores for a biomolecular simulation called NAMD, and scaling up to 16,000 cores. And so each one of these is a factor of 2, so you'd hope that the time per step would go down by a factor of 2. There are 3 different load balancing schemes. One where you don't pay any attention to the topology at all in this blue gene P, which is a 3-dimensional torus. One is where you have topology aware, 2 different schemes of being aware of the topology, and you see, unless you pay attention to the topology, if you do, you scale. You get perfect speedups, and if you don't pay attention to the topology, the load balancing doesn't work, and it stops scaling when you hit 4,000. Okay, so that is a too quick summary of Charm++, which is a widely used load balancing system. So, final slide. There's a big design space for different load balancing schemes. And I've tried to give you a tour of all of these. And there's a trade-off between locality and load balance. You can't have both at the same time. And there's many papers, many algorithms, many systems. And so what you need to do if you're worried about load balancing your scheme, your algorithm, is you have to ask, am I going to worry about shared memory versus distributed memory? Am I going to scale up to thousands of processors? What is causing my load imbalance? Do I have to worry about all the tasks being, having dependencies, or are they independent? What's the communication costs? And how am I going to trade off, locality versus, caring or not caring? So let me end with an open question, which is when people started worrying about load balancing, they thought that all of the imbalance is going to come from the tasks, right? This subtree is more expensive than that subtree. Maybe they were using a heterogeneous collection of machines because it was slow processors and fast processors. But they didn't worry about that on supercomputers. On very large-scale machines, it was a uniform machine, and all the cost was coming from the different tasks. Some people think that's going to change. That even if you have a single supercomputer, like the next generation of Hopper or a few generations away, the machines inherently is going to be so heterogeneous or irregular inside of it, processors are going to break. Things are going to run at different speeds for different reasons, that even regular problems are going to need dynamic load balancing. That you can't trust just because somebody tells you, I've given you 100 processors over here, those 100 processors are not going to necessarily run at the same speed of the 100 processors in a different part of the machine, even though they're supposed to be the same. So let me close with one funny story about a supercomputing talk a number of years ago, which I think won a prize. They were trying to diagnose a load imbalance on just such a machine. And it was supposed to be completely uniform, but it was a uniform machine and a uniform job. But it was terribly load imbalanced. By using all of these tools and taking a long time, they discovered that on every 16th processor, every once in a while, a daemon woke up to do some system job. And it completely slowed down every 16th processor once in a while to do some operating system task. And so that was an easy thing to fix. They had to sort of turn off that particular daemon in the operating system. But this is not necessarily going to be totally under our control anymore. As we scale up to these huge machines, you may have these out of your control events that occur. So And I think I'll stop there.